Thank you all for joining us today for the Clean in Place System Optimization webinar. My name is Jackie Slatt, and I'm the Marketing Director at eTech Group. In today's webinar, we're going to be going over the who, what, where, how, and why of CIP optimization. Before we dive into that, I want to do a quick introduction to who eTech Group is and introduce our presenters today. eTech Group is proud to be the 2025 System Integrator of the Year with Control Engineering and Plant Engineering. We are one of the largest system integrators in North America and headquartered in Westchester, Ohio. We have over 700 resources located throughout North America and across the globe, with more than 550 engineers and 30 locations across 10 countries and 3 continents. We offer a global scale with localized support. eTech Group is a technology agnostic partner with experience and expertise that allow us to make an impact from the top floor to the shop floor with our clients. We vet our technology partners across all layers of the technology stack to ensure our clients have the best solutions in the industry to draw upon. Today, we're joined by Frei, Director of Engineering at eTech Group. He's a licensed professional engineer. Hans brings deep expertise in automation and controls with a strong focus on batch control, CIP optimization, and the system integration process in intensive systems. He's known for aligning automation strategies with regulatory and operational goals, making him a trusted leader in the field. Hans is joined by Jeff Ballard. Jeff is a business development manager and a seasoned automation professional with a proven track record in modernization, Industry 4.0 adoption, and large-scale project leadership. Jeff brings a broader industry perspective, including deep experience in water and wastewater, OEM, and end-user environments, all of which benefit from smarter CIP strategies. Thank you, Jeff and Hans, for being with us today. And with that, I'll hand it off to Jeff to go into what a clean in place system is.
So CIP, or a clean in place system, is an automated method of cleaning an inside or an outside of a system, right? So a system of pipes, vessels, any kind of equipment that is used to produce any kind of food or beverage, or it could be pharma or life science product. It's used an automated control of water and chemicals and rinses to clean basically a system an end user uses to produce anything that we would touch or consume.
So looking at the CIP systems, there are married between a process side and then an automation side of it. From a process physical side, it's usually broken down in a series of tanks and pumps and pipes. And then that system then has a capability of injecting chemical, making sure it has a water supply, has heating capabilities, and so forth to be able to provide that to the equipment to be able to CIP. Then from the control side, that's broken down into a series of repeatable phases, steps, etc., that can be used to execute those CIPs to be effective in cleaning those different types of circuits on the system. So the organization of that from a controls perspective is you have a CIP skid, which controls the delivery of that solution, be either fresh water, be a wash solution and heated, etc., is going to be from the skid, but then it's going to be attached to different circuits. You usually have one CIP skid, and then you can be distributed out within a facility to provide that solution to multiple circuits or multiple pieces of equipment within the facility. So this way you don't have to have a CIP skid for every piece of equipment. And then those circuits then have different types of CIP. There's different flavors depending upon what your current product is in the system, based on what you're going to try to move to or what that regulatory requirement is. You may just have to have just a rinse, to remove that large foreign previous material from that system, or you might have a wash, or maybe you have an extended wash to help prepare the system more thoroughly for the next product, or maybe it's going to be down for a little bit. Then each one of those washes are then broken down into phases. And so most of the time when we develop CIPs, we're trying to think of them as like a batch system. If we're doing batch, we're going to create modules or equipment set up such that we can build the system to be very effective in what it's doing, and then utilize that repeatedly rather than having to build a separate instance of that phase every time that it's run with different types of circuits or washes. And so we break down those that washes into separate phases, where you have a rinse phase and a wash phase, and those washes could be either with a caustic or an acid or a sanitizer. And then those rinses can be set up basically to work repeatedly throughout, regardless if it's a pre-wash or a post-rinse wash or maybe your final wash, but try to use that so that we have it broken down into modular components. And then each one of those phases is then breaking down even further into individual steps. And so there's a goal for the phase, I'd say for a wash phase, to wash the system, but there's going to be a series of steps that have to be established to accomplish that within the controls. And so there's going to be steps in there, and then those steps will have interlocks or permissives that will have to be fulfilled before it can move on to the next step, and then proceeding through that. And then sometimes you'll have additional steps for different types of equipment, if it's more complex or less complex, and be able to handle that within that system. So talking about that further, why do I have some of these requirements in my CIP? So why do I heat? So the purpose of heating is actually for most instances, is to reduce how long that CIP is. Heating usually takes place during your wash steps. And so by injecting energy through the form of heat, that makes that wash chemical more effective by being warmer, and so decreases the amount of residence times that solution has to interact with your system, and then thus reducing how long it has to actually run with that solution in contact with your piece of equipment. There's also flow requirements. So the flows that are required for certain systems are not just pulled randomly out of the air. There's typically two different pieces that a flow requirement will come into play within a system. One is, what is the size of the pipe that we're trying to clean or that we're flowing liquid through? And then two, do I have any spray balls that are required to help effectively clean my tanks that are going to be inside the system, or vessels? And so the larger the pipe, the larger the flow. And the reason why that has to be the case is because we want to create a flow where the flow is mixing through the pipe as it's flowing. So you have to hit a certain velocity of flow that will essentially cause that mixing behavior within the flow of fluid itself. So then that contact of the pipe itself is continuously refreshed by a different set of solution as it moves through there, and is more effective. And then on the spray ball side of it, not all spray balls are built the same. Some of them can be set up for low flow or low pressure. Some of them are more like a jet. Other ones are just kind of like a sprinkler, just wetting the surface, etc. And so those spray balls are going to have a similar pressure or flow requirement to be effective in maintaining that fluid contact. Cooling is, although it doesn't seem like it's really all that necessary, but it is really essential for the life of the equipment. It's more for making sure my equipment is ready to be used again. And so I'll have a nice picture in a later slide that can show the more dramatic side of a ineffective cooling method. But essentially, we want to just not let cooling be up to whatever the environmental forces are. We want to actually do it in a manner which will protect our equipment. There are different types of CIPs to handle stuff more effectively or less effectively. And so, I mentioned you might just have a pre-rinse, and that's just to remove that previous product from the solution without really doing any deep cleaning. But you may have shorter CIPs because the moving from one product to another might have different requirements. The frequency of the CIP is going to be depending on your product, and also regulatory bodies that are involved within the particular products or within your facility. And so, think of it as, hey, maybe I'm moving from a sugar to a non-sugared product. Well, in that case, I'm going to probably have a more intensive CIP to remove that in there. Or if I have allergens like eggs or dairy or nut remnants, I'm going to need to be able to have a more effective CIP to remove those, so I don't transfer on those allergens to the next product that I'm trying to run. And then also the different products have a different shelf life within your system. If you have a more acidic type of solution, it's going to be able to last a little bit longer through a production run, whereas a less acidic type of system where the bacteria will easily more grow on the product. And so you're going to have to increase your frequency of your CIP to make sure that you keep those bacteria growth at a minimum. Another one that comes up is, what does the different types of chemicals actually do in my CIP? So the caustic is the agent that does the real washing. It is going to remove that build up or remove that product from the walls or the surfaces of your equipment, and kill that bacterial growth from the equipment. It's going to do the actual washing, and the concentration or type of caustic is going to be very dependent upon what type of products you run in your facility. The acid, on the other hand, is not there for cleaning. It's more for equipment longevity. And so when you're dealing with like stainless pipe, you need to run that acid system in there that helps reestablish that oxidized layer of that stainless metal to be able to increase the longevity of your equipment. And so when acid is introduced, it strips a little bit of that oxidized layer off. And then when air comes back in after that is done, then it's able to reestablish that oxidized layer with that equipment and helps that stainless equipment to last even longer. Sanitizer, I would say this is my least favorite chemical to have to work with because of the complexity that it usually encounters when trying to run a CIP. But a sanitizer does not require heat. It helps kind of like a quick way to kill any residual stuff in the system, but not really need to do an actual product run. Or sometimes sanitizer is introduced in the system and allows it to just sit in solution so that you can keep a system ready for a production run, but it might be hours, days later that it actually needs to run. And so you can keep it under a sanitized solution to facilitate that. A lot of reason why I don't like sanitizers, it has a tendency to foam really bad. And whenever you introduce foaming in pumps or spray balls, it has a very interesting combination that has to be managed with your liquid solution.
Why should we pay attention to optimizing a CIP system, right? I mean, it is sometimes kind of an afterthought, but one of the biggest things is the cost, right? So just like Hans had said, you're going through raw materials, right? You're going through caustic, you're going through chemicals, and especially you're going through water. And also it's the time that it takes to clean your system, right? So those are two incredibly important things within any time within a facility. The next biggest thing, and we hear this a lot, is sustainability, right? Your output can't just go straight into the sewer, right? There's a lot of chemicals in it. It has to be treated. If you could be more sustainable using better chemicals, using less chemicals, and optimizing the system, you're just going to be better off in the long run, right? And so also from there we come within compliance, right? So Hans hit on a couple things, right? Allergens, whether it's a compliance with it in the biotech or the pharma industry. And then from there, a lot of times that CIP is a standalone, what we call a standalone system, right? So there may be a knowledge gap, or there may be that system may not be as well known as the rest of the system. And that can lead to what we call Band-Aid fixes. So having us come in and optimizing that system and even incorporating it into your SCADA just makes it run a lot smoother. And in the end, it's going to be a lot less headaches. So if we optimize a CIP system, right, there's, again, less downtime, which is a scary word within a facility, right? So faster changeovers and more uptime, right? Which leads to cost savings, reduced water, reduced energy consumption, reduced chemical usage. We're within a lot of sustainability, or any kind of, depending on where we are in the country, there can be different laws and regulations. And then there's all kinds of compliance and quality issues. You know, it could be FDA, it could be life science, it could be some sort of validated environment like life science. And then also what we can do is we can optimize that system, and we can integrate it into the SCADA and the MES and actually pull that data and show in real time and in real data it's using less, it's taking less time, and it's optimized.
So how can this be done? How can we go through and optimize a system? And so we have a proven record on how this can be done. First one is we just need to know what that system does, right? We want to not just assume we know what that CIP system is trying to do or what it's trying to accomplish, but actually go in, look at the logic, look at the path that it's taking, interview operators and maintenance and so forth, and document what is this system trying to do? How is it doing it? What does those interlocks look like? What does the set points of those interlocks look like? And then provide a full package of documentation to show this is what the system is trying to do. And so then once we know what it's trying to do, then we want to see where those pieces along the way can be improved and optimized on. One way we want to shadow those operators as they begin to run a CIP and make sure that they have the knowledge or they're reminded of how to set up a CIP properly before it runs. And so this way, they feel, oh, I forgot to hook up that hose, or I forgot to open up that manual valve. Well, maybe they need to have better indication of what needs to be done for each one, because maybe all your CIPs have different little nuanced changes that have to be done before it can even run. What is, is there any mode that like a piece of equipment has to be put in? And then what is interlocks on that piece of equipment to ensure that it can actually do that? What is the instrumentation? Have they been calibrated recently? Are they providing you accurate information? The signals coming back to the PLC, are they truly representative of what is showing at the localized meter? What are those different potentials for optimizing? There's kind of 3 or 4 different ways that we can categorize where that optimization can take place. Logically, is it just simply changing some of the steps in the sequence to be more effective in liquid management or heating, etc.? Or maybe there's a mechanical thing that we need to flag and think about making corrections to, because you have a valve or a pump that's not performing correctly or was never meant to handle a specific chemical. And visually, like the indication, not just how to set up a CIP, but when it's running, well, why isn't it not proceeding forward? Do the operation and maintenance know why it's stuck on a step? Or why did it malfunction? Is there proper indication to accurately inform your personnel on what the CIP is doing? So looking at the inefficiencies that we have come across typically within our systems is, heating. That's a big one. Like, we get the feedback from our customers, like, it takes forever to heat this system. And well, we can look in there like, well, first off, what does the heat have to get to? What temperature does the system have to get to? And what temperature is the heating actually being told to go to? If they're, both at 150, man, it's going to take a long time to get there because there's going to be environmental loss. Well, maybe we need to give it a little bit higher set point. So then if we're trying to interlock at 150, well, we're going to tell it to heat to 155. So this way we can account for those environmental losses as that solution is going through that extended loop, and then be able to still sustain that set point that's required. Or maybe you have an interesting loop within your system, and you need to think about either preheating or shutting down part of the circuit temporarily to actually get the temperature and then open up that circuit appropriately, so then it doesn't take an extended amount of time to actually heat. Or maybe your heat exchanger itself needs some maintenance work on it. It's just not effective. It's got scaling, or the steam or heating method is just not performing how it was originally set up. Another one is chemical concentration. There's 2 sides to the chemical concentration. One is I'm trying to get to a high concentration for a wash requirement, or I'm trying to dilute it down to a low set point on a rinse solution. And so looking at the wash side, a lot of times chemicals, I'm just going to dump it in all at once. Well, the problem with that is then you just get this gigantic plug flow of chemical concentration that's extremely high throughout your circuit. But then what happens is it's going to have to rotate through that entire closed loop of your wash circuit to stabilize back down to the operational level, or maybe you don't have enough. And so then you have to then dose more in there. So one strategy is to kind of meter it in, like pump a little in, wait, pump a little in, wait. And so you're kind of encouraging that solution to already get pre-mixed in that system, rather than just trying to dump it all in at once. Another one with on the rinse side of it is, essentially a lot of times it's just dilution is a solution. Well, for CIP, that is not an effective way of doing that. The reason why is that's going to take a lot of rinse water to actually get that dilution to be effective to get you down below. Another strategy is just to limit how much water is in the system before you rinse. Maybe we do a drain or we pump stuff down to a minimum so that we eliminate how much wash solution is there before we go into a rinse step. And so this way we set up that step so that we're trying to plug that system, that wash solution out back to the exit drain. And in this way, we reduce how much water is being used on a rinse. And then what is the concentration limits of the equipment? I mentioned spray balls and sanitizer. Maybe we need to discuss it with your chemical supplier. Like, hey, what is the actual effective chemical concentration should I be doing for this type of CIP, and making sure it's not higher than is necessary. And then you can save chemical in that regard. Liquid management, and that's probably the biggest one that I've seen, is just poor liquid management of a CIP system. We don't need to have it fully saturated, tanks filled all the way up to the top, etc., because that's a lot of liquid to have to be sustained. So we want to provide set points on tanks, on different pipes, and etc. That is going to get us enough liquid to have that contact, but not an excessive amount that I'm going to have to add more chemical on my washes, or I'm going to have to add more rinse water to actually clean it back out again. We want to be able to have enough liquid to sustain that closed loop. We'll say, well, I'm losing a little bit of liquid. We'll have a little bit higher set point for that liquid loss on a closed loop because I have to have a door open on a tank and etc. But we'll anticipate that and be able to have enough to sustain that rather than having to have an abundance of liquid and then have to have less efficiencies on preceding steps. Spray balls, I mentioned that earlier. We want to have spray balls that are effective than just like dribbling down. No one wants to be in the shower and has to dance in the shower because they got low pressure. Same thing for a CIP. We want to get that spray balls at sufficient velocity and power that they're really cleaning those walls of those tanks and they're able to go all the way down. Another reason why to keep your liquid level low on the tank is so that the spray balls can do what they're intended to do. If you have a gigantic reservoir of liquid at the bottom of the tank that's going up halfway of your walls, well, now the spray balls are not actually touching the walls of that tank, and you're not getting that constant renewal of liquid across the surface of your tank, and it's probably not going to be nearly as effective as it could be. And then maximize those features of the CIP skid, right? If you have a circuit that's set up for preheating, let's take advantage of that and get that initial dosage of solution on your CIP skid up to temperature before it gets moved out to the circuit you're trying to clean. Maybe you have liquid recovery. We are able to have a tank dedicated to capture the caustic wash from a previous CIP and save it in the tank, and then reuse that for the pre-wash or a pre-rinse for the next CIP, that we can then not have to use quite the same level of chemical concentration on my wash because I've already hit it a little bit with a caustic solution. And maybe I have a dedicated wash tanks as well. Maybe you have a 3 or 4 tank CIP system where I have a tank dedicated to a caustic, a tank dedicated to acid, and I can get those up to concentration prior to requesting that liquid into my circuit. And so then I have even more time saved on my CIP. And I had mentioned earlier about cooling, right? Here's a prime example of what can happen if don't have controlled cooling, because most of the vessels within a facility are designed for pressure. If they're designed for pressure, they're typically not designed for vacuum. So the problem is if I have an unsustained, uncontrolled cooling on my system going from hot to a cool rinse liquid, what can happen is I can form a vacuum in there because my volume of air contracts with that cooler temperature being added in there, and suddenly I pull this vacuum and it can suck it in. And so we want to make sure that we don't introduce those type of problems with a CIP and make sure we control effectively. A case study that we had with CIP is I had a customer and they had a newly commissioned system with a CIP, and they're like, man, it takes like 2 to 3 hours to run this CIP. And sometimes it takes 2 or more times to rerun the same CIP before quality will pass it along. And so they were taking entire shifts sometimes of running CIP. So they're running it 2, 3, 4 times before quality would say, yeah, it actually was effective this time. And they didn't even know what the CIP did. No one knew what steps it was doing, how it was moved through the pieces of equipment on this skid. And so what we did is, first off, we examined and we documented it. Said, hey, this is what it does now. We looked at that like, okay, let's rearrange this sequence a little bit to have better liquid management, better understanding on how to clean each piece of equipment throughout the system. Then the sequence is updated. We tested that thoroughly to make sure that it was doing exactly what we wanted it to do. And then we turned it over to operation to see how it would work. And let me remind you, this was just logical changes. We did no physical changes on the system. There was no changes of pumps or valves or pipes or anything. It was just looking at it from a PLC perspective, and then providing some better documentation of what was happening on the HMI so that we understood what step was at. When all was said and done, after going through that, we increased on average 5 to 7 hours for production. So much increase in production that the skid actually started remaining idle. Like they didn't know what to do with it. Like other parts of their facility couldn't handle that much more production, so it would actually sit idle. And they could think about how to increase other parts of the facility for more production capability. The water and chemical usage was dropped by at least 2/3. Large part of that was we reduced the CIP time from 2 to 3 hours down to under an hour. And in addition to that, then the effectiveness of that 1 hour CIP was at 95% passing. And so they were able to run the CIP with confidence once, and then quality would come in and check it, and it was ready to go. The reason why the 95%, they had one nasty product that had just a scent portion of it that was just really hard to remove. And so that would require an additional CIP on occasion, and why it was not closer to 99 to 100%. But when it's said and done, the customer is just extremely happy with the result of this, because there was just a logical change on this system to be able to be more effective, liquid management, to reduce the amount of chemical, the amount of water, and then they're able to think about more future capability on the skid because of the increased production time. So what are the possibilities of a fully automated CIP? So from an operational standpoint, we want the operators not to have to babysit a CIP skid. They want to be able to set it up, hit start, and it does its thing and finishes. We don't want them to have to constantly come back and look at it and see why it's not running, why is it stuck, why is it leaking all over the place, or hey, shoot, I didn't set it up correctly, now I have to restart it again. We want to have that for the operators. We want it to be predictable, right? We don't want to have to just sit there and wait for how long is this CIP going to take before I can actually be done. We want to know, hey, it should take about an hour. Well, we want to count on that. And then we can then plan better for production and for operations to be able to take that CIP back, that skid back into production environment. We want to be able to pass. We don't want quality to have to come back over and over and over again and then have to use up their valuable time to check the CIP after multiple runs. We want them to come in, check it, yep, it looks good, and then they can move on to check other things within the facility. And also have proper acknowledgments, so reminders, hey, how to set it up correctly. You know, I typically include, you know, when we're dealing with chemicals, that, hey, make sure I'm good to add chemicals, that the area is safe, everyone knows that chemicals going to be added. And so have some prompts in there that will help operations be more aware and better aligned on how that system should be running. Other side is maintenance, right? They're usually the ones that are calling in when it's not working correctly. We want to give them as much visibility information to know, hey, why am I not running? Oh, I'm not at set point on my temperature. Okay, why is that the case? Oh, someone shut the steam off. All right, turn the steam on, away we go. We want to give that as much information on those interlocks and those permissives and make that very apparent on that interface on the HMI, so maintenance knows what that is and can troubleshoot it effectively and quickly. And then reporting, right? We want, ideally, reports are not just valuable for proving that it was clean, but also a trend, right? if we have reports, we can say, hey, it looks like I'm taking a little longer on my temperature. Why is it taking longer to heat? We go in and do an investigation and figure out what's starting to, what might need some work to fix a valve, or maybe my steam pressure suddenly dropped a little bit, of some of those natures. And we want to be able to have a report. We can see where our baseline was at of a good optimized CIP, and now where we're at now, and see, oh, why didn't it not work? Let's figure out the root cause of that. Instead of now having a new band-aided system, we want to be able to go back to that efficient baseline by using reports for that valuable piece of information.
Thank you, Jeff and Hans, for being with us today and sharing a little insight. We hope you guys found this useful. And if you have any questions or would like to speak with Jeff or Hans about how we might be able to help your CIP system, please reach out. Thank you.